Cement is kind of the glue that holds concrete together. And concrete is used more than any other material on the planet other than water.
You've probably marveled at the Great Wall of China, an incredible feat made possible by a crucial binding agent, cement. Every day, we witness new structures rising, from schools and hospitals to roads, and none of it would be possible without cement. In this video, we'll guide you through the entire process of how this essential material is made. The evolution of cement through the ages. Cement's story begins long before the Renaissance or the Industrial Revolution, stretching back thousands of years to ancient civilizations. The earliest known use of cement dates back to around 2500 BC, when the Egyptians used a type of cement made from gypsum to construct their iconic pyramids. This early cement wasn't quite like what we use today, but it served as a crucial binding material in some of the world's most enduring structures. Fast forward to around 300 BC, and we see the Romans take cement technology to new heights. They developed a material known as Roman concrete, which combined lime and volcanic ash to create a remarkably strong and durable substance. The Pantheon and aqueducts are just a few examples of Roman engineering marvels that still stand today, thanks to this early form of cement. The volcanic ash used, known as pozzolana, gave Roman concrete its unique properties, including the ability to set underwater, something that would be critical in later developments. As history progressed, cement technology saw incremental improvements, but it wasn't until the 18th century, during the Industrial Revolution, that a significant leap occurred. Britain, driven by its expanding empire and the need to protect maritime interests, faced the challenge of constructing lighthouses on perilous coastal rocks. The constant threat of losing merchant ships and warships propelled innovation forward. In 1759, John Smeaton, while building the third Eddystone lighthouse off the coast of Cornwall, made a pivotal discovery. He found that a mix of lime, clay, and crushed slag from iron making produced a mortar that could harden underwater. This was a groundbreaking moment in the history of cement, laying the groundwork for more advanced materials. But the story didn't end there. In 1824, Joseph Aspdin, a British bricklayer, took Smeaton's discovery further. He created a new material by firing a finely ground blend of clay and limestone until the limestone underwent calcination. Aspdin named it Portland cement because the concrete made from it resembled the esteemed Portland stone used in construction across England. While Aspdin's cement was an innovation, it wasn't yet the modern Portland cement we recognize today. That milestone was reached in 1845 when Isaac Johnson fired a mixture of chalk and clay at much higher temperatures, between 1,400 degrees Celsius and 1,500 degrees Celsius. This process, known as clinkering, produced minerals that were highly reactive and provided the cement with much stronger binding properties, paving the way for the cement we use in modern construction. Now that we've journeyed through the rich history of cement, it's time to see the raw materials that make modern cement possible. Ever wondered what goes into that powerful substance binding our world together? Let's break it down. Cement raw material. Portland cement, the most widely used type of cement globally, is a meticulously crafted chemical blend. It primarily consists of lime, silica, alumina, iron, and small amounts of magnesium oxide, sulfur, and alkalis. But what does that really mean? There are 4 fundamental compounds essential in the raw mix: calcium carbonate, silica, alumina, and iron oxide. These ingredients are finely ground into tiny particles to increase their reactivity. Once ground, they're blended together and fed into a colossal kiln, where they're heated to extremely high temperatures. A typical raw mix contains about 80% calcium carbonate and 12.5% silica. The remaining portion is primarily iron oxide and alumina, crucial for the burning process in the kiln. Without sufficient iron oxide and alumina, the mixture wouldn't combust properly, making these compounds indispensable. But the story doesn't stop there. The raw materials used in cement production aren't pure compounds. Take limestone, for example. It's predominantly calcium carbonate, but often contains varying amounts of silica, alumina, and iron oxide. Sometimes, magnesium carbonate sneaks in as an impurity. Besides limestone, other calcareous materials used in cement manufacturing include chalk, marl, and even oyster shells found near coastal areas. Argillaceous materials like shales, clays, slates, and blast furnace slag, rich in silica, alumina, and iron oxide, are also used. Sand is often a concentrated source of silica, while bauxite and iron pyrites are added when the raw mix needs more alumina or iron oxide. No two cement plants have the exact same raw mix design. This variability stems from the diverse compositions of raw materials available. For instance, one plant might use a blend of 70% limestone and 30% clay, while another might mix 95% chalk with 4.5% silica and 0.5% iron oxide to achieve the desired chemical composition in the raw mix. The key is to maintain consistency in the final product, regardless of the raw material sources. Proportioning or blending the raw materials is a critical step in cement manufacturing. Frequent quality control checks are essential to ensure the raw mix remains consistent. Adjustments are made as needed to keep the chemical composition just right, ensuring high-quality cement every time. Pre-processing of raw material. Before raw materials can be transformed into cement, they must first be extracted and prepared. The journey of making cement starts at the quarry. As earlier discussed, the primary raw material for Portland cement is limestone, but other essential ingredients come from secondary materials like clay or shale. These materials can vary widely, from soft, water-dispersible chalks to the hardest of marbles. To get these materials, the quarrying process begins with removing the overburden, the layer of soil and rock that sits on top of the deposit. This is achieved using equipment such as bulldozers, drag lines, and various types of motor shovels, selected based on the depth and nature of the overburden. Once the overburden is removed, drilling and blasting are employed to break up the rock deposits. Explosives are carefully placed and detonated to fragment the limestone and other materials, making them easier to handle and transport, as the quarry site is always some kilometers away from the plant site. After blasting, the resulting chunks of raw material need to be reduced to a manageable size for further processing. This process is referred to as the size reduction process. The materials are fed into crushers, which break them down into smaller pieces, less than 100 mm in size. This is a crucial step because it ensures that the material is small enough to be fed into the next stage of production. Typically, primary and secondary crushers are used for this purpose. For wet materials, the crushers might be replaced by a combination of wash mills and crushers. The equipment has evolved over the years, but the fundamental principle remains the same: reduce the raw materials to a size that can be efficiently processed in the grinding mills. On average, it takes more than 1.5 tons of raw materials to produce 1 ton of Portland cement. The grinding mills then further reduce the size of these materials, preparing them for blending and homogenization. With the raw materials now crushed and prepared, the next step in the cement production process is blending and storage. This ensures that the mix is consistent and ready for the critical stages that follow. The process of blending raw materials is complex due to the variability in the components. Unlike some materials that are uniform, cement production relies on a mixture of diverse ingredients, each contributing different properties. To create the perfect blend, we need to combine these materials in precise proportions. In many plants, raw materials are stored separately and fed into the grinding mills without pre-blending. This system requires meticulous adjustment of feeders and frequent sampling of the ground material to ensure the correct mix. However, this approach often leads to more extensive blending after grinding. To streamline the process, some plants use pre-blending systems. These systems help achieve a more consistent raw mix before it even reaches the grinding stage. There are two main types of pre-blending systems: batch pre-blending and continuous pre-blending. Batch pre-blending involves stacking all raw materials to create a pile that reflects the overall composition of the raw mix. This pile is then reclaimed and sent to the raw mill, ensuring that the materials are well mixed. Chemical composition is carefully monitored through feed-forward control to maintain consistency. Continuous pre-blending, on the other hand, involves feeding raw materials directly from bins to the raw mill. This system eliminates the need for stacking and reclaiming, and instead relies on real-time chemical analysis and feedback control to adjust proportions on the fly. Blending systems, especially batch pre-blending, are designed to address medium-term chemical variations that can occur in raw materials. By filtering these variations effectively, they ensure a more consistent mix and reduce the need for extensive homogenization after grinding. With our raw materials perfectly blended, it's time to move on to a pivotal step in cement production: processing the raw mix in the raw mill. This stage is crucial for transforming the blended materials into a fine powder that's ready for the kiln. The raw mill is where the real magic happens. Here, the blended raw mix is ground into a fine powder, known as raw meal, which is essential for the next stage of cement production. This process involves several key steps and technologies to ensure the raw mix is processed efficiently and effectively. There are two main types of raw mills used in cement production: ball mills and vertical roller mills. Each has its own method of grinding and advantages, but the most commonly used is the VRM. The grinding process in the raw mill involves several key steps. The raw mix, which is a blend of crushed limestone, clay, and other materials, is fed into the mill. Inside, it's subjected to high-pressure grinding, where the raw materials are broken down into a fine powder. During this process, the raw mix is constantly moved and mixed to ensure uniformity. The goal is to achieve a very fine powder with a consistent chemical composition. This fine powder, known as raw meal, is essential for the clinker formation. Controlling the temperature and airflow within the raw mill is critical. Proper temperature management ensures that the raw meal achieves the desired fineness and quality. Airflow systems help in transporting the ground powder and separating fine particles from coarser ones. Cyclones and baghouses are used to collect dust and separate fine particles from the airstream. This helps maintain a clean environment and ensures that only the finest particles are sent to the next stage. Quality control is an ongoing process during raw meal production. Samples of the raw meal are regularly tested for chemical composition and fineness. This ensures that the raw mix meets the required specifications and will produce high-quality cement. Pyroprocessing, the heart of cement production. Pyroprocessing is the fiery heart of innovation, where the magic of cement production truly happens. This is where raw meal is subjected to intense heat, undergoing a transformative journey that turns it into clinker, the essential building block of cement. This process, which combines high-temperature chemistry with sophisticated machinery, is the heart of cement manufacturing. The process involves several key stages: preheating, calcination, clinker formation, and cooling, each driven by complex chemical reactions and sophisticated machinery. The journey begins with the preheater, a critical piece of equipment where raw meal is initially subjected to preheating. Inside the preheater tower, raw meal is exposed to hot gases from either the kiln or cooler. This heat transfer raises the temperature of the raw meal to approximately 850 degrees Celsius. Preheating the raw meal is crucial as it reduces the energy required in the rotary kiln, making the entire process more efficient. By preheating, the raw meal is better prepared for the high-temperature processing that follows. Once preheated, the raw meal moves into the calciner. Here, at temperatures around 900 to 1000 degrees Celsius, significant chemical transformations occur. One of the key reactions in the calciner is the decomposition of calcium carbonate, a primary component of the raw meal. This decomposition process converts calcium carbonate into calcium oxide and carbon dioxide. The release of carbon dioxide prepares the calcium oxide for further reactions in the rotary kiln. The calciner plays a vital role by handling approximately 60% of the total fuel burn, effectively reducing the thermal load on the rotary kiln. Following the calcination process, the partially calcined raw meal enters the rotary kiln, the heart of pyroprocessing. Inside the rotary kiln, which operates at temperatures ranging from 1400 degrees Celsius to 1500 degrees Celsius, further chemical reactions take place. The raw meal undergoes transformations to form key clinker minerals. These minerals include tricalcium silicate, which forms from the reaction of calcium oxide with silica and significantly contributes to the cement's strength development. Another mineral, dicalcium silicate, forms from calcium oxide and silica at higher temperatures and enhances the cement's long-term strength and durability. Additionally, tricalcium aluminate forms from calcium oxide and alumina, affecting the cement's setting time and early strength. Tetracalcium aluminoferrite, created from calcium oxide, alumina, and iron oxide, contributes to the color and overall performance of the cement. As the raw materials fuse together to form clinker nodules, these need to be cooled rapidly and effectively. This is where the clinker cooler comes into play. The clinker cooler is a crucial component in the cement production process. After exiting the rotary kiln, the clinker is extremely hot, often reaching temperatures of around 1,200 degrees Celsius to 1,400 degrees Celsius. Rapid cooling is essential to maintain the quality of the clinker and prevent unwanted reactions with moisture or other substances. The clinker cooler utilizes ambient air or preheated air from the kiln to bring the temperature of the clinker down to approximately 100 degrees Celsius to 150 degrees Celsius. The cooled clinker is then transported to clinker silos or hoppers directly by conveyors for storage and later for the cement grinding process. The hot air in the cooler is recirculated back to the rotary kiln for reuse, which further saves the energy consumption of the cement plant. This cooling process not only solidifies the clinker, but also helps in reducing its temperature to a level suitable for subsequent handling and grinding. Why is cooling important? The cooling of the clinker serves multiple important purposes. Firstly, it prevents the clinker from reacting with moisture, which can lead to issues such as unwanted hydration or the formation of undesired compounds. Secondly, cooling ensures that the clinker maintains its desired chemical and physical properties, which are critical for the quality of the final cement product. Lastly, the cooler recovers some of the heat from the clinker, which can be redirected to preheat the incoming raw meal or used elsewhere in the production process, enhancing overall energy efficiency. In essence, pyroprocessing is a high-stakes chemical and mechanical ballet where raw meal is meticulously transformed into clinker. Final processing and packaging. After the clinker has been properly cooled, the final phase of cement production involves grinding it into a fine powder and incorporating various additives to produce different types of cement. This phase is critical for defining the final properties of the cement, such as its strength, setting time, and durability. The hardened clinker is fed into grinding mills, which pulverize it into a fine powder. The grinding process, just like raw mix turned into raw meal, is typically carried out using either a ball mill or a vertical roller mill. In a ball mill, steel balls inside a rotating drum collide with the clinker, breaking it down into a fine powder. Alternatively, a vertical roller mill uses large rollers to crush the clinker between a rotating table and stationary surfaces, which can be more energy efficient than traditional ball milling methods. The fineness of the ground clinker is crucial for the performance of the cement. The particle size distribution affects the rate at which the cement hydrates and gains strength. Finer grinding increases the surface area of the cement particles, which enhances their ability to bind with other materials and improves the overall strength and durability of the cement. Once the clinker has been ground to the desired fineness, various additives are blended in to produce different types of cement tailored for specific applications. One of the primary additives used is gypsum, which regulates the setting time of the cement. Gypsum slows down the hydration reaction, allowing sufficient time for mixing and application before the cement sets. In addition to gypsum, other additives are used to enhance the properties of the cement. Pozzolans, which can be natural or artificial, react with lime in the cement to form additional binding compounds. This reaction improves the cement's durability, resistance to chemical attacks, and overall strength. Common pozzolans include volcanic ash and fly ash. Ground granulated blast furnace slag, GGBS, is another significant additive. It is a byproduct of iron production and is used to improve the cement's durability and reduce its permeability. Slag cement is particularly beneficial in environments that are exposed to chemical attacks or in large-scale concrete applications due to its lower heat of hydration. Silica fume, a byproduct of silicon and ferrosilicon alloy production, is also added to. Enhance the strength and density of the cement, It contributes to improved resistance to chemical attacks and adds to the overall durability of the cement. In some cases, limestone is incorporated into the final cement mix to produce a more cost-effective and environmentally friendly product. Limestone can improve the workability and finishing properties of the cement. The blending of these additives is precisely controlled to ensure that the final product meets the desired specifications. Modern cement plants use advanced technologies for automated blending and real-time monitoring. These systems continuously adjust the quantities of additives based on quality control feedback, ensuring consistency and adherence to precise standards. After blending, the cement is stored in silos before being packaged. As the cement production process nears completion, the final step involves packaging and storing the manufactured cement. This phase ensures that the product remains in optimal condition until it reaches the end user. Once the cement has been ground to the desired fineness and mixed with any necessary additives, it is conveyed from the grinding mills to storage silos. Storage silos are large, typically cylindrical structures designed to keep the cement dry and protected from external contaminants. These silos are equipped with advanced monitoring systems to maintain the quality of the stored cement by controlling factors such as temperature and humidity. When it's time to distribute the cement, the stored product is either packed into bags or shipped in bulk. For smaller quantities, cement is often packed into durable, high-strength bags. The most popular cement packing machines for this purpose are roto-packers. These machines are renowned for their efficiency and speed, capable of packing large volumes of cement quickly. They work by filling bags with a precise amount of cement and then sealing them to ensure they remain airtight. For larger-scale distribution, cement is shipped in bulk. This method is commonly used for significant construction projects or large-scale commercial orders. Bulk cement is transported by trucks, rail freight wagons, or ships, depending on the destination and logistical requirements. Each transportation method is chosen based on factors such as the volume of cement to be shipped, distance to the customer, and infrastructure availability. Environmental issues in cement manufacturing. Cement manufacturing, while essential for construction and infrastructure, poses several environmental challenges affecting air, water, and land resources. Air pollution is a significant concern, originating from multiple sources within a cement plant. The grinding and handling of raw materials generate dust, which can affect air quality. The kiln operations and clinker cooling processes further contribute to air contamination by releasing additional dust and harmful emissions, including oxides of sulfur and nitrogen, hydrocarbons, aldehydes, and ketones. The cement grinding, handling, packaging, and shipping operations also contribute to dust generation. Of these, the kiln is the primary source of dust emissions in cement plants, with its high-temperature processes exacerbating air pollution. Water pollution is another critical issue, primarily arising from interactions between water and kiln dust. The leaching process, which removes soluble alkalis and recovers insoluble materials for reuse, is a notable source of water pollution. Additionally, wet disposal methods, where dust is managed as a slurry, contribute to the contamination of water bodies. The use of wet scrubbers to collect kiln dust from exhaust gases can also result in water pollution if the scrubber effluent is not properly managed. The storage of kiln dust, raw materials, clinker, and coal on plant premises can lead to land and water pollution. Rainfall runoff from these storage piles can carry pollutants into adjacent water sources if adequate runoff management practices are not implemented. This runoff can significantly impact local water quality and ecosystems, further compounding the environmental effects of cement production. The economic impact of cement. The economic impact of cement is profound and multifaceted, influencing a range of sectors from construction to manufacturing, and even impacting global trade and job creation. Cement plays a crucial role in the infrastructure development that underpins modern economies. As a primary ingredient in concrete, it is fundamental to the construction of roads, bridges, buildings, and other critical infrastructure projects. The demand for cement often reflects the level of economic activity and growth, with increases in construction projects driving higher consumption of cement. the cement industry is a significant contributor to global employment, providing jobs across various stages of production, including quarrying, manufacturing, and distribution. In developing regions, the industry often represents a substantial source of employment and income, supporting local economies and contributing to community development. The industry's capacity to generate jobs extends beyond direct employment, creating additional opportunities in related sectors, such as transportation, logistics, and machinery manufacturing. From an economic perspective, cement also has a considerable impact on trade. Many countries export cement to meet international demand, contributing to their trade balances and supporting economic growth. Conversely, countries with a high demand for cement often import it, influencing their trade deficits. The global cement market is competitive, with major producers vying for market share in different regions. This competition drives innovation and efficiency within the industry, leading to advancements in production technologies and sustainable practices. The cost of cement has a ripple effect on the broader construction industry. As a major component of concrete, fluctuations in cement prices can impact construction costs and, consequently, the overall expense of infrastructure projects. This sensitivity to price changes affects not only builders and contractors, but also the end consumers, influencing housing affordability and infrastructure development budgets. Investment in the cement industry often involves substantial capital expenditures, including the construction of new plants, the upgrading of existing facilities, and the implementation of advanced technologies. These investments can stimulate economic activity by creating construction jobs, generating business for equipment suppliers, and fostering technological advancements. Additionally, sustainable practices and innovations within the industry, such as the development of alternative cements and energy-efficient production methods, can lead to long-term economic benefits by reducing costs and minimizing environmental impacts. Moreover, the economic impact of cement extends to environmental considerations. The industry is a significant source of carbon dioxide emissions, which has prompted efforts to mitigate its environmental footprint. Investments in greener technologies and practices not only contribute to sustainability, but also create new economic opportunities in the field of environmental management and carbon reduction. Biggest cement manufacturers in the world. In the world of cement manufacturing, a handful of giants dominate the industry, shaping the skylines and infrastructure across the globe. These companies not only supply vast quantities of cement, but also drive innovation and set industry standards. Among the leading cement manufacturers is LafargeHolcim, the world's largest cement company, formed through the merger of France's Lafarge and Switzerland's Holcim. With a global footprint that spans over 70 countries, LafargeHolcim plays a crucial role in providing essential materials for both residential and commercial construction. Another major player is Cemex, a Mexican multinational with a strong presence in over 50 countries. Cemex is known for its high-quality products and innovative solutions in building materials, including cement, concrete, and aggregates. Heidelberg Cement is also a significant force in the cement industry. Headquartered in Germany, it operates in more than 50 countries and is renowned for its extensive range of cement products. China National Building Material Group Corporation, CNBM, is one of the largest cement producers in China and the world. As a state-owned enterprise, CNBM benefits from significant resources and infrastructure, enabling it to meet the massive demand for cement in one of the world's largest construction markets. Lastly, Anhui Conch Cement, based also in China, is another major cement manufacturer with a substantial market share. Known for its robust production capacity and commitment to quality, Anhui Conch Cement is a key player in both domestic and international markets. Thanks for watching. We'll see you in the next video.